In the last lecture, we were looking at forced convection at high Peclet number, that is Taylor dispersion, axial dispersion in a pipe, okay, axial dispersion in a pipe. So, I had explained to you the physical meaning of this axial dispersion by looking at two cases. The first was the case of a plug flow and the second was the case of a laminar flow. Okay. So, if you had a plug flow, the velocity is a constant across the entire cross section, okay. And therefore, if you inject a pulse at some x location, okay, if you inject a pulse at some location x location in a plug flow, that pulse is going to travel downstream at a constant velocity throughout the cross section, and any spreading of that pulse will occur only due to molecular diffusion. In contrast, for a laminar flow, the velocity is 0 at the walls and a maximum at the center. If I inject a pulse at some x location, that pulse is going to have a maximum velocity at the center and 0 velocity at the walls. So, it is going to spread something like this, okay, and that results in a greater axial spreading due to convection, okay. It is called dispersion, that is spreading due to convection is what is called dispersion, okay. So, it spreads much faster. In fact, as the velocity increases, the spread is faster still, and so you will see later that we will get the paradoxical result that as the Peclet number becomes larger, the dispersion coefficient actually is proportional to the inverse of the Peclet number, okay. Normally, the diffusion ratio of convection and diffusion is the Peclet number. So, you would expect diffusion to be proportional to the Peclet number. In this case, you get it as the inverse. And we looked at it under different approximations. The first one is that the Peclet number is large based upon the pipe diameter and the average velocity. And at any downstream location, the concentration variation across the cross section is much smaller than the average concentration, okay. At any downstream location, the concentration variation across the cross section is much smaller than the average concentration. Related to that, that is length by that condition is valid when the length by diameter ratio is much larger than the Peclet number, and note that the Peclet number is itself large in this case. And finally, the length scale for variation in the axial x direction is much larger than the diameter. Diameter is the length scale for variation in the radial direction. The length scale for variation in the axial direction is much larger than the diameter. So, how do we do this calculation? This is the concentration diffusion equation, okay. Note that the velocity is only in the x direction. So, you have only the convection in the x direction on the left side, and there is diffusion in both the radial and axial directions on the right side in a cylindrical coordinate system, where D is capital D is the diffusion coefficient, molecular diffusion coefficient. We had written the velocity as the velocity in a pipe is given by this expression 2 V average into 1 minus r by r the whole square, that is the parabolic flow in a pipe, maximum velocity at the center, 0 velocity at the walls where r is equal to capital R. The maximum velocity at the center is 2 times the average velocity in a pipe flow, okay. The maximum velocity in the center is 2 times the average velocity. We had separated out the velocity into an average part plus a what we call a fluctuating part, okay. That is the average is just the cross section average, the plug flow, plus a component that varies across the cross section, okay. So, if you plot the component that varies across the cross section, it will be negative at the walls and it will be maximum at the center, okay. This velocity plus the plug flow velocity will give you the total velocity, okay. So, this was the velocity fluctuation, V average into 1 minus 2 r square by r square. Similarly, the concentration variation was also separated into 2 parts. One is the average concentration, cross section average concentration, and the second is the fluctuation about that cross section average. The average concentration is 1 over the cross sectional area into integral from 0 to r of the differential area in the radial direction. Okay. The differential area in the radial direction is 2 pi r dr into the concentration. Okay. Similarly, the average velocity is also the integral over the cross section of 2 pi r dr times the velocity divided by the total cross section area. The implication of this is that the cross section average of these fluctuating velocities is 0. Okay. If the cross section average of the concentration is the average concentration, and if I subtract out that average concentration from the total concentration, I get C prime. Therefore, the cross section average of C prime has to be 0. Similarly, the cross section average of Vx prime also has to be 0. Okay. So, we are writing the concentration and velocity as the sum of two parts. One is the cross sectional average plus the difference between the actual value and the cross section average. Okay. Those are written with primes, the latter is written with a prime. Okay. Then we wanted to know what is the cross section average flux, because in Taylor dispersion we ultimately want to calculate what is the cross sectional average flux in order to determine if there is a variation in the concentration along the length, what is going to be the flux generated due to that. Okay. In this case, I had previously missed out a minus sign. Okay. So, this is equal to minus times the diffusion coefficient, because mass goes from higher concentration to lower concentration, and that is the cross section average of the local flux at different locations in the cross section. Just as the concentration was the cross sectional average of the average concentration was the cross sectional average velocity is the cross sectional average flux is also the cross sectional average as shown over here. Okay. And so, we were trying to calculate this flux. Okay. It consists of a convective part, okay, plus a diffusive part, and from that I subtract out the average convective part, because if I write a concentration equation only for the average concentration, okay, I will get an equation of the form partial CAV by partial T plus VAV CAV is equal to D effective partial square CAV by partial Z square, partial x square, I am sorry, the axial direction. Okay. This is the equation for the average flux, that is the dispersion along the axial direction. I have one contribution here due to V average times C average. So, I have to subtract that out from the total flux. So, now expressing the concentration in terms of the average part plus the total part. Okay. If I express the concentration in terms of the average part plus the total part, I will get this as V average C average plus V average C prime. Okay, so, let me remove this and write it in some more detail. D in this case is the molecular diffusion coefficient, because we are writing the local flux. Okay. Minus V average C average. Okay. And you can see that these average parts will cancel out. Okay. The other thing, recall the assumption that the concentration fluctuation about the average is small compared to the average concentration itself. Okay, we said one of the assumptions that we stated over here was that the concentration variation across the cross section, okay, you can see it over here, concentration variation across the cross section has to be much smaller than the average concentration. Okay. So, on account of that, okay, we can also neglect partial c prime by partial x over here. Okay. Okay, we can also neglect partial c prime by partial x compared to partial of c average by partial x. Okay. Now, the average flux J average is equal to 1 by pi r square integral 0 to r 2 pi r dr into V average c prime plus V prime c average plus V prime c prime, okay, minus d partial c average by partial x. Okay. That is the expression for the cross sectional averaged flux. Okay. Now, consider this term. Okay. V average is an average cross sectional averaged velocity. Okay. Okay. If you consider this first term here, 1 by pi r square integral 0 to r 2 pi r dr into V average c prime. Okay. Now, V average does not vary with r, okay, it is a cross sectional averaged. Okay. So, therefore, this term I can take out of the integral, okay, and write this as V average times this integral of c prime over the cross section. Okay. And this integral of c prime over the cross section is 0. Okay. We had just seen that we had defined the concentration in such a way that the integral of c prime over the cross section is equal to 0. Okay. Okay. Therefore, this term is equal to 0. Okay. And similarly, this V prime c average only depends upon x and t, it does not depend upon r. So, once again c average can also be taken out and the integral of V prime has to be equal to 0. Okay. Any function that is linear in the fluctuating quantities, either V prime or c prime, has to be 0. This term is in general not 0, okay, because it contains the product of two fluctuating quantities. Okay. This term is in general not 0 because it contains the product of two fluctuating quantities. Okay. And finally, the last term is also independent of r because it is the derivative of c average with respect to x. So, the cross sectional average of that will give you the same thing. Okay. So, therefore, the expression for the flux is 1 by pi r square integral 0 to r 2 pi r dr into V prime c prime. V prime is a function of r, c prime is a function of r, minus the molecular diffusion coefficient partial c average by partial x. Okay. So, that is the expression for the average flux. And now, we have to calculate this term. Okay. We have to calculate this integral. Okay. Within this integral, we already know what is V prime. Okay. V prime is the difference between the actual velocity and the average velocity. We do not yet know what is the expression for c prime. So, if we find out the expression for c prime, substitute it in here, we will get the average flux, and from that we will get the dispersion coefficient, okay, the effective dispersion coefficient. Okay. So, how do we do that? We have to calculate this from the conservation equation. Okay. Note the conservation equation, okay, partial c by partial t plus V x partial c by partial x is equal to d into 1 over r plus partial square partial square c by partial x square. Okay. And now, for c I have to substitute C average plus C prime, and for Vx I have to substitute V average plus Vx prime. Okay. So, this first term becomes average, so rather I will write it again. Okay. Plus V average plus Vx prime partial of okay. The next step is to take the average of this whole thing over the cross section of the pipe. Okay. So, if I just take, if I take this equation, okay, and then integral, okay, 2 pi r dr times the equation. Okay. Okay. You can see that all the linear terms in C prime will go away. Okay. All the linear terms in C prime will go away, and therefore, I will have partial C average by partial T plus V average partial C average by partial x. Okay. On the right side, I will have d into 1 by r d by dr of r partial C average by partial r plus partial square C average by partial x square. Okay. So, any term that is multiplied that is linear in C prime or Vx prime will identically go to 0. Okay. However, you have this term here. Okay. You have this term here. Okay. So, let me just write that out separately. Okay. One by pi r square integral 0 to r 2 pi r dr into V average partial C average by partial x plus V prime partial C average by partial x plus V average partial C prime by partial x plus V prime partial C prime by partial x. Okay. Okay. And you can see that these two terms will go away because they are linear in V prime and in C prime. Okay. These two terms are linear in V prime and in C prime. Okay. The only term remaining is the V average times C average partial C average by partial x, which I have shown you over here, okay, plus a term due to the fluctuations, the product of fluctuations 1 over pi r square integral 0 to r 2 pi r dr into V prime partial C prime by partial x. Okay. So, this is what I get when I do the cross section average of the concentration field. Okay. So, this is the original concentration field. Okay. And this is the cross section average. Okay. From the original concentration field, I can subtract out the cross sectional average. Okay. From the original concentration field, I can subtract out the cross sectional average, and I will get, okay, an equation for the fluctuation, partial C prime by partial T. Okay. Plus V average partial C prime by partial x plus V prime partial C average by partial x. Okay. Minus this term. Okay, I am subtracting out this term here. Okay, this minus this term. Okay, minus 1 by pi r square integral 0 to r 2 pi r dr V prime partial C prime by partial x. Okay, the cross sectional average of the fluctuating velocity times the fluctuating concentration. Okay. And this is equal to, on the right side, okay, I will write it below here, okay, d into 1 by r partial by partial r of r partial C prime by partial r plus partial square C prime by partial x square. Okay. So, this is the equation we have to solve for the concentration field. Okay. So, this is the equation that we have to solve for the concentration field. Okay. In this equation, recall the assumption that we had made. Okay. Recall the assumption that we had made, that is that at any downstream location the concentration variation across the cross section is much smaller than the average concentration. C prime is much smaller than C average. Okay. C prime is much smaller than C average. In this term here, I have Vx prime times partial Vx is partial C average by partial T. All of the other terms are proportional to C prime. Okay. All of the other terms are proportional to C prime. Okay. Therefore, I can neglect all of these terms. Okay. This term proportional to C prime, this term proportional to C prime, and this term proportional to C prime in comparison to V prime times partial C average by partial x. Okay. So, I can neglect all the other terms in comparison to partial C average by partial x. That is assumption number 2 that we had made. Okay. Assumption number 3, length scale for variation in the x direction is much larger than the diameter. Okay. If the length scale for variation in the x direction is much larger than the diameter, the derivative is much smaller. Okay. If the length scale for variation is larger, the derivative is smaller. So, I can neglect partial square C prime by partial x square in comparison to 1 over r d by dr of r partial C prime by partial r. Okay. So, now I have only these two terms in the equation. Okay. This convective term plus the diffusion in the radial direction. Okay. Based upon the approximations that the concentration variation is much smaller than the average concentration. Okay. On that basis, I had neglected partial C prime by partial x and partial C prime by partial x in comparison to partial V by partial x. Note that V prime is not small compared to V average. Okay. V average is V prime minus V average is 1 minus 2 r square by r square. Okay. Okay. So, therefore, on that basis I get an equation for the concentration field Vx prime C partial C average by partial x, okay, is equal to d by r partial by partial r of r partial C prime by partial r. Okay, I get an equation for the concentration. Okay. Vx prime, recall, was equal to V average into 1 minus 2 r square by r square. It was the difference between the parabolic velocity profile and V average. Okay. Partial C average by partial x is a cross sectional average. So, it is independent of r. Therefore, I can solve this equation quite easily. Okay. You just have to integrate 2 times with respect to r where you have this R dependence over here. Okay. And you get an equation for C prime. C prime is equal to V average by D into R square by 4 minus R power 4 by 8 R square plus 2 integration constants, those turn out to be C1 log of R plus C2. Okay. Obviously, constant C1 has to be 0 because the concentration has to be finite at R is equal to 0, that is a symmetry condition. Okay. C1 has to be 0 because the concentration has to be finite at R is equal to 0. Okay. So, that is a symmetry condition. Okay. And you can evaluate C2 from the condition that integral 0 to R, okay, 2 pi R dr times C prime, this has to be equal to 0. Okay. This condition, average of the concentration fluctuation has to be equal to 0, can be used to evaluate this constant C prime. Okay. I am sorry, this constant C2. And finally, I will get expression for the concentration. C prime is equal to V average by D into R square by 4 minus R power 4 by 8 R square, okay, minus R square by 12 into, okay, I am sorry, I should, okay, so this, okay, this term should also be included here. So, I get a partial C average by partial x plus C1 log of R plus C2, okay, and this term is 0 and C2, okay, gives you the constant C2. So, this is the expression, okay, partial C average by partial x. That is the expression for C prime, okay, that is the expression for C prime. Okay. So, now we have got C prime, okay, there is no prime here, okay, and we have got the velocity. So, let us go back to our expression for the average flux. Okay. Let us go back to our expression for the average flux, which is this one, okay, which is this expression. Okay. J average is equal to 1 by pi R square integral 0 to R 2 pi R dr into C prime into V x prime. Okay. Minus the diffusion coefficient partial C average by partial x. Okay. We have to substitute the expressions, okay, is equal to 1 by pi R square integral 0 to R 2 pi R dr into the expression for C prime V average by D, okay, into R square by 2 minus R power 4 by 8 R square minus R square by 12. Okay. Okay. Partial C average by partial x, okay, that is C prime, and V x prime is V average into 1 minus 2 R square by R square minus D partial C average by partial x, okay, where D in this case is the molecular diffusion coefficient. Okay. In this case, D is the molecular diffusion coefficient. And I have to do the integral of these two functions which are dependent on the radius. Okay. These two functions are dependent on the radius, I have to do the integral of that. You can see that the integral turns out to be V average square by the diffusion coefficient times partial C average by partial x. Okay. And finally, I will get the expression as J average is equal to minus V average square R square by 48 D partial C average by partial x. Okay. That is obtained by doing this integral. Okay. That is obtained by doing this integral. Okay. Minus the second term, minus the diffusion coefficient partial C average by partial x. Okay. I can take the partial C average by partial x outside. Okay, into diffusion coefficient plus V average square R square by 48D. Okay. R is equal to D by 2. So, I just get minus partial C average by partial x into D plus V average square R square divided by 192 times the molecular diffusion coefficient. So, the effective diffusion coefficient is equal to D plus V average square R square by 48D, okay, which I can also write this as the diffusion coefficient into 1 plus V average square D square by 192 D square. Okay. It's equal to the diffusion coefficient into 1 plus P Beckley number square by 192. So, this is the dispersion coefficient, and as you can see here for Taylor diffusion this goes as 1 over as this goes as Beckley number square. Alternatively, from here you can see that this component, the dispersion coefficient component, is proportional to 1 over the diffusion coefficient. If diffusion coefficient is larger, the dispersion coefficient is smaller, and vice versa. Okay. So, this is the calculation of the Taylor dispersion coefficient. It goes as Beckley number square, okay, times the molecular diffusion coefficient, or as, okay, if it is a convection dominated flow, the Beckley number is large, therefore, this will be the largest term. Okay, this will be the largest term, and this is proportional to V average square D square by the diffusion coefficient. So, the dispersion coefficient goes as 1 over the diffusion coefficient in this case. With this, I will complete our discussion of forced convection. In the next lecture, I will proceed to examine natural convection. We will look at different scenarios for natural convection, what are the dimensionless numbers, dimensionless groups, and so on, and I will derive the equations for you for natural convection. I will continue that in the next lecture. I will see you then.